So one example of wave interference that's particularly relevant for mechanical waves are standing waves. And so standing waves are produced when you have two identical waves that interfere with each other as they're traveling in opposite directions in the same medium. An easy way to get this to happen is to have waves that reflect off of endpoints. If I have a wave that's traveling across a medium and it hits some boundary point and bounces back, then what I will have is the opportunity for two identical waves, both the initial wave and the reflected wave, to interfere with each other as now they're traveling in opposite directions within the medium. And there are a couple distances that we care about for standing waves. The first is the wavelength of the wave. And so here what we're going to emphasize is the wavelength of the wave. If we start at this edge, goes up, crosses that center line again, goes down, comes back up. If we think about our standing wave pattern as it's pictured here, what we see is that the wavelength contains two humps. And so the up and down for both the blue and red wave that creates our standing wave pattern means that the wavelength is represented by two humps. That's going to be an easy way to sort of think about things going forward. The second distance that we care about is, well, what's the length of the medium? So whether we're talking about a string or a column of air, there's some length of that string or column that will also be important in terms of figuring out what's going on with the standing waves that we can generate within the medium. Two other terms that we want to go ahead and introduce at this point are nodes on the one hand and antinodes on the other. So nodes are basically the points where there's no displacement of your wave, so where your standing wave still sits along the center line. Antinodes are just the opposite. These are points of maximum displacement within the pattern. They're the position in your pattern represented by peaks in the two waves. The first standing wave patterns we want to talk about are between two closed ends or fixed ends. And our best example here is, again, this is the kind of standing waves that you can set up on a guitar string. So one end of the string is fixed over here, the other end of the string is fixed over there. So again, the length of our string is all the way across. Just from a labeling perspective, we can talk about each of these as harmonics. So the first harmonic, you'll notice, has a single hump. One hump goes all the way across the string. That's also known as the fundamental. The second harmonic has two humps, and so it's described by n equals 2. It also happens to be called the first overtone, but the important detail is that the number that represents the harmonic is the same as the number of humps that are sitting in your pattern. So the third harmonic has 3 humps. The fourth harmonic has 4 humps. The fifth harmonic has 5 humps within the standing wave pattern. So if we want to come back and think about each of these, again, one of the lengths we said we were going to care about was the length of the string in this case. One hump is half the wavelength. So the full length of the string for our first harmonic is equal to half the wavelength, which means the wavelength of this standing wave is twice the length of the string. So you would need an entire second hump sitting over here that would also have the length of the string to complete the wavelength. For the second harmonic, the length of the string is the wavelength of the standing wave. So again, you've got 2 humps within the pattern. Starts, you've got up and down, come back. So your 2 humps here tell you that you've got a full wavelength across the length of the string. So lambda is equal to L. For the third harmonic, basically what we see is we're breaking up the length of the string into one full wavelength plus another half. So that's our 2 humps get us a full wavelength, and we've got 1 left over. So we've got 3.5 wavelengths here. So if we solve this for the wavelength of the wave in our third harmonic, it's twice the length of the string over 3. Fourth harmonic. Well, now what I see is I've got 2 humps, that's 1 wavelength, 2 humps, that's the second wavelength. So the length of the string in our second harmonic is 2 full wavelengths. Solving this tells me that the wavelength here is half the length of the string. And then we can play the same game for the fifth harmonic. And again, what we see is with our 5 humps, we've got 1 full wavelength, a second full wavelength, and a half wavelength left over. So we've got 5.5 wavelengths across the length of the string. So I can solve this, and it tells me that the wavelength of the fifth harmonic is 2L over 5. If we think about each of these options, our first harmonic we can think of as 2L over 1. L is 2L over 2. So the second harmonic was 2L over 2. Third harmonic, 2L over 3. The fourth harmonic was 2L over 4, which ends up being the same as L over 2. The fifth harmonic, 2L over 5. So the pattern that I notice is that for all of these standing waves, the wavelength of the standing wave is equal to 2 times L over whichever harmonic you're interested in looking at. And so if you want the first harmonic, 2L over 1. The second harmonic, 2L over 2, or that's just L. And you can keep going for whatever nth harmonic you're interested in thinking about the wavelength of your string. So that's for a closed standing wave pattern. I can also have an open standing wave pattern. And so a couple of examples for open standing waves tend to be with air columns within musical instruments. So pipe organs, the pipes themselves can be open air columns. A flute is an open air column. And so what you'll see here is that, of course, because it's open rather than closed, with our closed, we had a node at the end. With our open, we have an antinode at the end. But what we're going to do is we're going to say, well, I can cut this in half, switch the order of these two, and what I recognize is that I still have a single hump that's the entire length of my wave here for the first harmonic. So again, these labeled the same, that your first harmonic n equals 1, second harmonic, your first overtone n equals 2, third harmonic, fourth harmonic, fifth harmonic. So our open standing waves label the same way as our closed ones do. And in fact, they work out the same way, because when I rearrange my pattern here, what I recognize is this looks exactly like my closed standing wave pattern. I've just taken that hump, cut it in half, and put the center of the hump on the ends. With the second harmonic, same thing's true. So I have there's a half a hump, there's another half a hump, so there's one hump plus a second hump. So again, this is really just a full wavelength. I can also look at it as it goes from peak to trough to peak. So sure enough, the entire length of the string is one full wavelength. For the third harmonic, I've got 1, 2, 3 when I stitch these two together, so 3 humps again, just like I did in my closed pattern. Fourth harmonic, I've got 1, 2, 3, 4 humps. So again, this is really peak, trough, peak. There's one wavelength. Peak, trough, peak. There's a second. So again, the full length of the string is 2 wavelengths. Fifth harmonic, 1, 2, 3, 4 in the middle, and then I've taken that fifth hump and split it up. And so what you see is I get exactly the same pattern for my open standing wave as I had for my closed standing wave. And so the wavelength of the nth harmonic is described by the same equation. So it's still 2L over n for my open standing waves, where n can again be 1, 2, 3, 4, pick any integer that you want. Where things get a little bit different is with my third standing wave pattern. So this is if I have one closed end and one opened end. Here we've set this up so the closed end is over here on the left and the open end is over here on the right. And so as an example for a closed open standing wave is the air column within a clarinet or a trumpet. In those cases, unlike with the flute that's open at both ends, because in a flute you're blowing across the top, in a clarinet or a trumpet, your mouth sits at one end. So that end is closed off, but obviously the instrument opens up at the other. The labeling is a little bit different because what you'll notice is we only have odd values. So the first harmonic is still the fundamental, but the first overtone for an open-closed standing wave is known as the third harmonic. The second overtone is the fifth harmonic. The third overtone is the seventh. So our overtones are still labeled the same, but we've lost the even values for our harmonics. Again, if we want to think about the structure here, closed at this end, opened at this end means that this is half of a hump, which is another way of saying it's 1/4 of a wavelength. So the wavelength for this standing wave, for my fundamental standing wave for an open-closed standing wave, its wavelength is 4 times the length of the medium. When I look at my third harmonic, I see a hump plus 1/4. So this is half a wavelength in the hump plus 1/4 of a wavelength over here. So this is 3/4 of a wavelength, which I can solve for lambda is 4L over 3. When we look at the fifth harmonic, 1 hump, 2 humps, so here's a wavelength plus 1/4. So this is 1 1/4 wavelengths for the distance across L, which means the wavelength is 4L over 5. Seventh harmonic, again we get 1, 2, 3 humps, so this is a wavelength and a half plus another quarter. So this is 1 3/4 of a wavelength for my distance L, and so the wavelength is equal to 4L over 7. For the ninth harmonic, 1 full wavelength, 2 full wavelengths, again plus 1/4, so this is 2 1/4 wavelengths is the length L, which means that the wavelength of the standing wave for my ninth harmonic is 4L over 9. And this pattern's pretty easy to see because it's basically 4L over the number of your harmonic. And so that's the expression we can use to calculate the wavelength of the nth harmonic for an open-closed standing wave. Is instead of being 2L over n and all numbers are available to us, it's now 4L over n and we can only use n's that are odd numbers.